dear participants from the various universities, institutes, research labs, and my dear students from the physics department at College University. Good afternoon to all of you. I welcome all of you in today's webinar, which is based on the energy traps in the atomic nuclei. Before we proceed further, it is my privilege to introduce Professor P.M. Walker. Professor Walker did his BA and MA from the Cambridge University and PhD from Australian National University. After completing the PhD from Australian National University, he spent almost his whole life in the University of Surrey, Guildford, UK. In 1992, in 1987, he joined as a lecturer in the Department of Physics, University of Surrey. Then he was promoted as a reader in 1994. In 1998, he was promoted again as a professor of physics in the Department of Surrey, University of Guildford. And 2004, he was heading the Department of Physics. And 2006, he was a William Penny Professor of Nuclear Physics in the University of Surrey. 2012, he was a Director of Research in the Department of Physics, University of Surrey. And since 2015, he's a Emeritus Professor in the same department, University of Surrey. I am proud to announce that Professor Walker visited almost 10 countries and leading labs of the nuclear physics in almost every country of this world. He has more than 420 research articles in the highly reputed journals and more than 80 invited talks. Professor Walker was awarded with the LM Medal by the European Physical Society, APS Outstanding Referee by American Physical Society. In 2019, as a Rutherford Medal and prize by Institute of Physics. In 2011, he was a CERN Associate and guest professorship from the Peking University of China. He has a membership award from the GSA Germany and William Penny professorship from AWE. He was holding the personal chair, University of Surrey. Above all, he is a very finest human being I met in my life. Professor Walker, I still remember the days spent with you during my visit in 2014 or 15, I think. And still I remember the guidance that you provided me during my PhD study through email, by sending me literature, through the Zoom calls, through other telephonic discussions. And today he will be discussing about the energy traps in the atomic nuclei. And along with this, in this talk, along with various types of the isomers that we are finding in the nuclear physics, he will be discussing about the application of the isomers and emerging opportunities in this area. I'm not taking too much time now. I request Professor Walker to start his webinar, please. Professor Walker.
Well, thank you very much for that nice introduction. It's a great pleasure for me to be here now, telling you something about nuclear isomers, which I've been working on for quite a large fraction of my life. I hope you can hear me all right. Is that?
Yes, you're audible.
So isomers are sometimes called energy traps. I hope that will become clear. The background picture is the University of Surrey, where I've spent the bulk of my career. The outline of my talk is there's a fairly long introduction about the nuclear landscape, historical notes mainly relating to isomers, the different types of isomer, and then isomers in what we call exotic nuclei, which are unstable nuclei going towards the edges of stability. And I will also have some discussion of isomer applications. And it's something we have to bear in mind that for those of us studying basic science, the applications can be important, and we need to keep an eye on that. And in that vein, I wish to remind you what Homi Bhabha said, that it is absolutely in the interests of India to have a vigorous school of research in fundamental physics, for such a school forms the spearhead of research not only in less advanced branches of physics, but also in problems of immediate practical application. So I won't ignore the practicalities of nuclear isomers. First, I wish to remind you that the atomic nucleus is very small. Well, I'm sure you're aware of this, but quite how small it is does take some thinking. It was in 1909 that Geiger and Marsden did a fairly short experiment. It was a summer project of Marsden, who was an undergraduate student in Manchester University at the time, bombarding foils with alpha particles. And he had some surprising results of the alpha particles coming back from the direction that they were sent into the foils. And this was a puzzle, and it took a couple of years for Rutherford to work out the solution, and he explained it in terms of the mass of atoms being highly concentrated in the center, which he called the nucleus. And there's something like 4 orders of magnitude difference in the scale of a nuclear size and an atomic size. And this is often represented by a picture like this with a nucleus and orbiting electrons, but the scale of the nucleus there is far too big. But it's difficult. If you represented it by its real size, then it would just be a minute dot in the middle, and it's amazing how much goes on in that nucleus. So this talk is concerned with how much goes on inside such a small space. The one way of saying it is a billionth of the volume of solid matter, yet it's 99.97% of the mass of solid matter. But let's carry on. There's the nucleus. You can blow it up and you can make pictures of it. You can't photograph it, not yet anyway, but you can draw pictures. But usually you see pictures that are lots of balls, 2 different colors. Oh yes, I forgot to mention that the last element of understanding what was in the nucleus was somewhat later. After the tiny size was realized. It was with James Chadwick discovering the neutron, which was an important component of the nucleus and makes up half, or usually slightly more than half, the mass. Okay, so for different numbers of neutrons and protons, we draw something like this nuclear chart, and you can see lots of tiny squares here. Well, the black squares represent the 300 stable isotopes, so I should really call them nuclides. It doesn't seem to be a very commonly used word, nuclide. It's probably more often they're called isotopes, although strictly speaking an isotope, well, I won't go into definitions at the moment. Anyway, there are 300 approximately stable isotopes represented by these black squares. But there are something like 3,000 that have been studied in the laboratory with varying half-lives, some as short as milliseconds, many living for years. And these are the stuff of nuclear structure physics, to understand the occurrence and the properties of these red squares, which we can make in the laboratory. And we're always developing new equipment so we can reach further into the unknown. And theoretically, the green area on this chart should be real nuclei that we would like to study. and there's something like 3,000 of those. So after 100 years of studying the properties of nuclei, we're about halfway through making all possible nuclei combinations of neutrons and protons. And part of the motivation to get further with this task is to reach further into this blue broad line, which represents the nuclei that are made in our process, nucleosynthesis. Broadly speaking, that's colliding stars, exploding stars, colliding black holes. These are the violent environments where such nuclei are made, and to understand the stuff of life, all the elements that we find on this beautiful earth that we live on, they're made in exploding stars. And to understand exploding stars, we need to understand nuclei out here in the unstable region that we haven't reached yet. So some of the accelerators around the world are exploring these as yet unknown regions of nuclei. But for each square on there, there's a whole world going on. And you can see in this representation of energy versus spin, or angular momentum. There's a whole space in there full of quantum states. And under some circumstances, there are secondary minima. And in these secondary minima, you can get long-lived excited states, and they're called isomers or energy traps. Energy traps for the fairly obvious reason that they're trapped in there for a long time, and it's due to the potential energy surface as a function of energy for some variable such as angular momentum. So it's states like this trapped at some higher excitation energy that I will be discussing. The story of isomers begins with Frederick Soddy in 1917. He proposed, he's the guy who came up with the idea of isotopes. So isotopes, as you know, have equal chemical properties but different masses due to the different numbers of neutrons in the nucleus. But Soddy proposed, it wasn't clear at the time that this could really be true, but he said we can have isotopes with identity of atomic weight as well as chemical character, which are different in their stability and mode of breaking up. So he clearly envisaged different states of given nucleus, given nuclide. It was a few years later that the first decent evidence appeared from the work of Otto Hahn in 1921, studying the alpha and subsequent beta decay of uranium. I won't go into the details here, but he basically found two routes that seem to go through the same mass and charge, and he said from his results that he seemed to have a dual decay, and such a case has not been observed before in radioactive transformations. So this was a perplexing situation, and people tried to study these states, but it turned out to be very difficult, and it was a while before there was any acceptance of such a concept. The breakthrough really was a theoretical breakthrough from von Weizsäcker. He's well known for his liquid drop model, the Bethe-Weizsäcker formula for nuclear masses. But when he was just 24 years old, he realized that angular momentum was an important parameter in quantum states. And if there were large changes in angular momentum involved, then this could lead to long lifetimes. And subsequently, we can look back with today's knowledge and see that this case of protactinium, the first isomer, actually it's a low angular momentum state that's the excited state, and a high angular momentum state is the ground state. It's an odd nucleus, and it can have such properties. But it wasn't well understood at the time, but it's remarkable how long it was from when Hahn discovered the first example and von Weizsäcker explained it, and then isomers became accepted. But I'm missing out that in about 1935, there was a proliferation of isomers from the new tools that were being developed, particularly by Fermi in Italy, scattering and the bombardment of various substances, foils, with neutrons, and the neutrons could excite isomers. But this long time between 1921 and 1936 was not idle on the nuclear structure front, and one of the principal debates was to do with electrons and beta decay and conversion electrons, which at the time were not known. And the key figures here were Charles Ellis and Lisa Meitner working independently. So Ellis was in Cambridge and Meitner was in Berlin, working with Otto Hahn, actually. So Berlin and Cambridge seemed to be the places where a lot of the work was going on. And the strange observations were that beta decay seemed to be associated with a continuous electron spectrum, but there were spikes at particular energies, which ended up being called conversion electrons. And this was an engaging time with different views, but now is not the time to go into the details. But let me point out that these conversion electrons, the spikes, were really the best early evidence for quantization of nuclear excited states. So these are quantum objects. You can't have continuous excitations. If you essentially heat up a nucleus, it's going from one particular state to another, and there's no intermediate states of nebulous energy. They're quantized, and these sharp spikes represent the quantization. Sharp spikes in the electron spectrum. Well, I'm talking about conversion electrons because they turn out to be quite important for isomers. The process is that the nucleus can lose its energy by interacting with the orbiting atomic electrons. The gamma ray never comes out. It's a virtual gamma ray in an interaction of the nucleus directly with an atomic electron, and the electron is ejected and carries away the nuclear excitation energy. And that can be a very dominant process, particularly for isomers. So now here's a modern representation of so-called internal conversion coefficients, the ratio of probability to emit an electron compared to a gamma ray. And for high angular momentum transitions, you can see that the probability of the nucleus decaying by electron emission compared to gamma ray emission can be overwhelming, like more than 10 to the 9 times as many electrons as gamma rays in particular states. So this can have a huge influence on decay rates. Let me give one example, which I find rather pleasing. It's associated with a storage ring at GSI in Darmstadt in Germany. And ions are sent circulating around the storage ring from high energy reactions, and all the electrons can be removed. So here's dysprosium 149 in a long-lived excited state, an isomer. It's labeled 66 plus. That means dysprosium has 66 protons. So to make it 66 plus, you have to remove all the electrons. So you could call those bare ions. And in this storage ring, you get a signal as the ions go round, and you can measure their mass and distinguish it from the ground state. And these are the decay away here can be interpreted as the half-life of these states, and it can be measured to be 15 seconds in this particular case. But if you study this in neutral atoms, you find it has an isomer with half a second half-life. There's a factor of 30, the half-life is extended by removing the electrons, and that's entirely due to its inability, with the electrons removed, its inability to undergo electron conversion, and the conversion coefficient is actually 28, marginally different from 30. So huge effect. The atomic electrons can have a huge effect on nuclear excited state lifetimes. We'll take a breath. Just something about the naming. The word isomers comes from chemistry. Chemical isomers can express this in various different ways, but basically chemical isomers are different physical arrangements of a given set of atoms. Nuclear isomers, you can say, are different physical arrangements of a given set of nucleons, neutrons and protons. Now, you might think of chemical isomers as the atoms are in fixed places, and the nucleons are certainly not in fixed places, they're orbiting around. So this is a property of angular momentum. This is a key feature in understanding nuclei, is the way angular momentum influences the structure. And any nuclear excited state, if on this basis of this first line, could be called an isomer. But it's usually taken to mean that there's some long about the half-life. There should be some reason that the half-life is rather long. Typical nuclear excited states have half-lives close to a picosecond. That's 10 to the minus 12 seconds. So when the half-life is a nanosecond or more, still a pretty short time, but it's long in the timescale of nuclear orbits, then we call it an isomer. And it's relevant to say, well, what about electrons going around atoms? They're a bit like nucleons going around in a nucleus. They can have metastable states. They're not called isomers. I don't know, there's a history of when we use words and when we don't, but the electronics excitations that live for a long time are called metastable states. And we don't hear so much about them, but they're there. We usually don't hear much about them because atoms bump into each other and they de-excite by collisions. And the metastable excitations of atomic states really come into their own when there's a very low density of atoms, such as in outer space, where atoms don't bump into each other very often. And then you can have very long-lived atomic states, such as clouds of hydrogen, they decay and emit low-energy photons with half-lives of, I forget now, thousands of years. So there's a whole physics of electronic metastable states, which is not the subject of my talk. For the range of isomers, I won't go into all of these, but let me point out that tantalum 180 has a half-life that is huge. It's so long it can't be measured. The decay of the isomer of tantalum 180 is far slower, or it has a half-life far longer than the age of the universe. Whereas other isomers can be very short-lived, a few nanoseconds, but may exist at high excitation energy, more than 10 MeV. At such high energies, neutrons and protons are in principle unbound, but they're held in by what one could call an angular momentum barrier. This is a very high angular momentum state. And then at the other extreme of energy, there's thorium-229, which has an excited state at just 8 electron volts, not millions of electron volts. This is now an atomic scale energy, but it's in the nucleus, and it's of particular interest for atomic clocks, as I'll come to at the end, or nuclear clocks. So these are some of the numbers associated with isomers in nuclei. I obviously can't describe them all in detail in a short talk. What I would point out is one general feature represented on the side here, that the ground state of a nucleus, the lowest energy state, can often decay. It might be stable, that's one of the 300, but if it's one of the 3000, it might decay usually by alpha particle emission or beta particle emission. An isomeric state might decay by alpha or beta particle emission, but in addition, it's got the option of gamma decay, internal transition, well, gamma or electron conversion. This is an electromagnetic process, and it only applies to isomers, not ground states, and it gives the thought that you might be able to influence isomeric states electromagnetically, such as shining a laser on it or shining X-rays on it. Can you make an isomer decay? Can you excite it? What can you do to manipulate isomers? So we'll come back to that point. But first of all, I'll be talking about the structure of isomers. There's something like 2,600 isomers known with half-lives greater than 10 nanoseconds. So this shows how their energy is found as a function of mass number. And one of the characters who has worked a lot on this is Ashok Jain. He published his Atlas of Nuclear Isomers, and I've had the great pleasure to work with Ashok, who for many years has been based at the Indian Institute of Technology in Roorkee, and I'm sure a number of you know him. You can see one of the important features of this plot is the occurrence of isomers is not random. And that's also shown on this plot of the nuclear chart with isomers superimposed. So the blue squares are the 300 odd, approximately 300 stable nuclides, and the red circles represent the cases where there are isomers with a restriction greater than 1 MeV in excitation energy and greater than 1 millisecond half-life. And it's very clear on this that the isomers are not randomly distributed. And the reason for the what we might call clustering or grouping of isomers on this chart has got a lot to do with the shape of the nucleus, whether it's spherical or deformed, and how the angular momentum couples to the deformation. The deformed regions are, I should say, these black lines represent closed shells, where spherical shape has particular favoring in the nucleus, whereas well away from the closed shells, such as here, deformed shapes are favored, and in this particular region there are a lot of isomers. So that gives us some clues that we need to look at nuclear structure in more detail, and it turns out there are roughly, you can subdivide these classes, but there are 3 principal classes of isomer. One is the spin isomer or spin trap, which was the type of isomer that was envisaged by von Weizsäcker, the first kind of isomer discovered, where it's the angular pocket in the angular momentum potential energy surface that causes the long half-life. But subsequently it was realized that if there's a deformed nucleus, then not only does the magnitude of the angular momentum matter, but it's also important what is the orientation of the angular momentum, because angular momentum is a vector quantity, and angular momentum in any isolated physical system, angular momentum is a conserved vector quantity, both in its magnitude and its orientation. In nuclei, it's even more important than linear momentum. So there are these kind of isomers that depend on the orientation of the angular momentum that are called K-isomers. I'll say a little bit more in a minute. And then thirdly, there are shape isomers where the nuclear shape can change in excited states, and the very fact that the shape changes can lead to long half-lives. And these were discovered a bit later, and there are quite a few examples now that are well established, particularly isomers that go to extreme nuclei that can have very highly deformed shapes before they fission and break into 2 pieces. Then on the way to fission, they can form elongated shape isomers called fission isomers. Examples are shown here in a bit more detail. The spin isomer with a long half-life and a high angular momentum due to the nature of the quantum angular momentum of the excited states. In the K isomer, we find that the angular momentum in this example is quite large, but in this one it's quite small and it still lives for 4 seconds. So we need to interpret this in terms of the orientation of the angular momentum. And then one well-known shape isomer, uranium-238, can decay by fission or back to the normal states with a big change in the deformation. But the reason for the isomerism isn't clear just giving those numbers. We need a little bit more information, and it's common to use estimates, so-called Weisskopf estimates of the half-life, which is based on an extreme single proton model. A proton orbiting in the nucleus will radiate. This is any charged particle being that's accelerating will radiate. And if you compare the measured half-life with the so-called Weisskopf estimate, you can work out a hindrance factor, the amount that it's slower. Well, these spin isomers actually obey the Weisskopf estimate rather well, and this seems to be a typical case, the hindrance is 1. That means the Weisskopf estimate equals the measured value for a high angular momentum transition. But if we look for this type of isomer called a K-isomer, we find that the Weisskopf estimate is hugely reduced. The actual half-life is hugely less than the Weisskopf estimate. The reduction can be by a factor of 10 to the 9, here 10 to the 13. So the reason for that is understood in terms of the orientation of the angular momentum. So it's actually when you look at the half-lives compared to a simple model that you can work out something about the reason for the half-life being what it is. And in the shape isomer, we again have a substantial hindrance, not quite as much as for the K isomer, but this is quite unusual actually. A lot of shape isomers have rather little hindrance. It seems to be a less robust form of isomerism. So that was an introduction to isomers. I'll say a few words about structure and then a few words about applications. So I'm going to dash through this rather quickly, but nuclei, excited states of nuclei can decay by a number of ways. They can decay by gamma ray emission, conversion electron emission, and illustrating the various ways you see data. So don't worry too much about the experiments and the details of the data, but we can measure gamma decay of isomers, electron conversion decay of isomers, thirdly, alpha decay of isomers, fourthly, far from stability, proton decay of isomers, fission decay of isomers, so the whole lot. Now, but in addition, there are some less obvious ones. If you look at laser hyperfine spectroscopy, you can see peaks belonging to isomers. It doesn't matter if the isomer decays or not. Laser spectroscopy, laser hyperfine structure, so this is how the atomic electrons are changing. The orbits of the atomic electrons are different when there's an isomer compared to in the ground state. And if you measure the mass, I've already alluded to that with the storage ring result, but you can use penning traps, and these devices are on a centimetre scale, a few centimetres across, or storage rings to measure the mass, where the circumference of the storage ring at GSI is 100 meters. A massive device, you can observe individual ions. So here's an individual isomeric ion going round and round in the storage ring as time progresses down the screen. And at some point, it gamma decays and goes to the ground state. Of course, all this has to be calibrated, but I can let you know after calibration that this mass represents an isomer and the ground state mass is represented a slightly different orbital frequency. And this had never been observed before from one ion. Well, in the storage ring experiment, there were about 17 ions of this mass found to represent the isomer. And then it was possible to go and do a more focused experiment that was more, produced more isomers once you know where it is. So here's a portion of the nuclear chart. The storage ring experiment started off with a gold beam and knocked bits off it, high energy, and made all the orange isomers. The new isomers were discovered, one of which was this tantalum-187 isomer. But that can be made from tungsten-186. Tungsten, the yellow squares are very long-lived, alpha decaying, near enough stable isotopes. So tungsten-186 is a stable isotope of tungsten, and if you bombard it with xenon, you can have multinucleon transfer reactions to tantalum-187. And so with some other recent experimental developments at a device called KISS, which is the KEK isotope separation system in Tokyo, we bombard the tungsten foil with xenon and stop the tungsten, the recoil products, amongst which is the tantalum, laser ionize it and separate them with a dipole magnet and generate and look at the electron and gamma decay. This is a rather quick tour through a bit of experimental detail, and it produces experimental spectra. So this is one of the key ones in the bottom of this slide. You can see lots of peaks which represent gamma ray transitions. You can measure their intensity as a function of time and find that this isomer, which had been discovered in the storage ring, has a half-life of 7 seconds. And the storage ring experiment, I find this quite intriguing. The storage ring experiment measured its energy, the excitation energy of the isomer, to be 1789 keV with an uncertainty of 13, and the gamma ray spectroscopy experiment, which is more precise, measured 1778 plus or minus 1 keV. So that's quite consistent, very consistent. And that produced level scheme structure from the gamma ray transition energies and all sorts of interpretation. So there's a whole world of nuclear structure to explore here, but I'm going to take the opportunity to change gear and talk about some of isomer applications, because I don't want you to think that isomers are purely for basic science. There are possibilities. Some of them are very challenging, perhaps will never be realized. But let's start with a couple of actual useful uses of isomers now. So they're not the subject of research as isomers, they're tools to do other things, but they are isomers. One is technetium-99 isomer. This is the most widely used so-called isotope, nuclide, for medical imaging. So I don't know how many of you have had medical imaging done with technetium-99 isomer, and it's particularly good. It emits 141 kV gamma ray, which is just good for getting out of the human body, but can be stopped with detectors and measured. there's no beta decay here, and beta decay electrons can do peripheral damage. There are some conversion electrons. The level structure is quite intriguing, but now isn't the time to go into it. But this is used for thousands, maybe tens of thousands of treatments every day around the world for learning about what's going on inside your body. Outside the body, but in very frequent use for research, is Mossbauer spectroscopy. Mossbauer was a famous physicist who discovered that you could have recoilless nuclear decay in a crystal, which led to extremely precise measurements. And if you, the most favored nuclide of all for this kind of study is an isomer in iron 57. Its half-life is rather short, 98 nanoseconds, but it's still significant in terms of getting good resolution in Mossbauer spectra. And here it decays by a 14.4 keV gamma ray. And next to it, alpha, that doesn't mean alpha decay, that means the conversion coefficient. So actually most of these decays, factor of 8.6, are from electron emission, not gamma emission, which does limit sometimes the sensitivity of the Mossbauer study, but that's a different story. So going to more speculative considerations, it would be nice to use isomers to make a kind of nuclear battery. And here we come to electromagnetic manipulation of isomers. Now, generally speaking, an isomer is long-lived, so you can't just knock it down to the ground state. There needs to be a quantum state, in an intermediate quantum state. And if that state is rather close in energy, then you can envisage shining 10 keV X-rays onto a long-lived isomer if there's a 10 keV quantum state above it. If it was below and it was excitable, then it wouldn't be an isomer, but it could be above and excitable and have a rapid transition probability. And then that might decay back down, bypassing the isomer. You have to find the right nuclear structure, but perhaps there would be such states, and then you could have a controllable energy store, which you could release the energy on demand. How close can we get to that? We will see in a moment, but just by way of conceptualizing it, nuclear fission has an energy scale of 1 or 200 MeV per fission. Chemical energies are around 1 electron volt per colliding molecules. And nuclear isomers were in the 1 MeV range, so a lot bigger than chemical energies, but somewhat less than fission, but still enough energy that you could imagine doing very interesting things if you could control it. So one of the popular ones to look at has been tantalum 180, because it's so long-lived you can dig it out of the ground. In fact, I discovered the other day there was a Times of India report just in March this year that tantalum has been found, I don't know how I should pronounce Sutlej River. So if you're quite close to that now, so you could drive up to the Sutlej and dig out some tantalum, and in that tantalum, which is mainly tantalum 181, you would have some tantalum 180, which would be in the form of an isomer. Now, attempts to de-excite that isomer have been various. A particular result was achieved in 1999 with 1 MeV photons, and it was possible to untangle the data to realize that there were particular quantum states being excited by these approximately 1 MeV photons. And that then the isomer would decay back down to the ground state. Well, this shows the principle. You can control the isomer half-life electromagnetically. You can speed up its de-excitation by exciting it, letting it decay down, but there's no return for this really. The net energy you get back per excitation is only 77 keV, but you've had to put in an MeV, and most of those MeV photons wouldn't achieve this excitation. The cross-section is too small. So this shows a principle, but it's not useful in practice. Question is there a case where low energy photons can be used to de-excite isomers? Well, there was a lot of excitement at a similar time, 1999, about the 31-year isomer in hafnium-178. There was supposed that there might be a K-mixing level, because this is a K isomer, and irradiations with 100 keV X-rays appeared to release this 2.4 MeV. Unfortunately, it's a complicated story. One aspect is that the K-mixing level itself has never been found. And then there have been mixed results and a failure to reproduce the original results. So in 1999 was the first report, Collins et al. In 2009, and 10 years later, one of the original authors showed that there was no significant effect and lowered the threshold significantly. But not to be defeated, there were some Bremsstrahlung measurements made by Kirishuk, published in 2015, and he's just published another paper about a possible new isomer in hafnium-178. So it seems like the hafnium-178 story still has a little way to go, but there's nothing dramatic being achieved in the way of de-exciting the isomer. One avenue is to think harder about electron conversion and look at the inverse, which goes the other way. If you capture an electron, you might be able to excite the nucleus. This is called nuclear excitation by electron capture. And that may be harnessed in certain conditions, and there's been studies with an isomer in molybdenum-93 where there's just a 5 keV excitation could release the energy of an isomer at 2.5 MeV. There's some data for this which were published in Nature in 2018, which appeared to show this bypassing route, and there was considerable excitement from that result. Unfortunately, so far this has not been reproduced, and it's been claimed theoretically that the result was a factor of 1 billion too strong. So this is a controversial area, but this paper's being published. I'm pretty sure there's another one being written at the moment, and to understand what is going on, what is causing the observed spectrum, maybe it's Coulomb excitation, but no breakthrough there yet, unfortunately. There are some other possibilities that are quite different for manipulating isomers. Have to be very quick with these, but first of all, cesium. It's possible for cesium to form a Bose-Einstein condensate. Cesium atoms, you can make it an atomic gas of cesium atoms at very low temperature, and it condenses into a single quantum state. The question is, what happens if the cesium atoms are in excited isomeric state. And this cesium-135, has a 1 hour, roughly, half-life isomer, which could be put into a Bose-Einstein condensate, and when it decays as a nuclear isomer, it might emit the gamma rays coherently because they're in a single quantum state. This is quite an exciting possibility, but it's not yet been tested experimentally, but there are tests underway in Finland. Then what it really seems to be working and is causing a lot of excitement is the low-lying isomers excited from the ground state, and the possibility of making a kind of nuclear atomic clock. And one case is scandium-45, and last year in Nature there was a publication pinning down the excitation energy precisely using the new, at the time, European X-ray free electron laser, and to manipulate this scandium-45 isomer. The real prize is the thorium-229 isomer, much lower energy, right? Not 12 keV, but 8 eV. And now this has been achieved with an optical laser, a special custom-built VUV laser, has pinned down this one in 2 different experiments. There's PRL published by Tito et al. Earlier this year, and a new one in Press by Elwell et al. With an agreement. So there's big excitement for learning about thorium-229 in hugely more detail, and working towards making a super accurate clock that could be used to test fundamental constants of nature and all sorts. It's a really different exercise, but very exciting. But time is gone. I'll just summarize by saying isomers were discovered approximately 100 years ago. They're key states in the study of nuclear structure, but they can also store huge amounts of energy, and there are exciting possibilities as to how one might use stored isomer energy. So thank you for listening, and a couple of extra reading items. In particular, it's about 100 years ago, and with Ashok Jain and Bhumika Maheshwari, we've edited a special issue on nuclear isomers in the European Physical Journal Special Topics. So if you Google nuclear isomers, EPJST, you will find a whole set of articles on nuclear isomers that's just become available. That's it. Thank you.
So thank you very much, Professor Wakar, for wonderful presentation. There are a certain set of questions from students first.
Yes, how do I hear the question?
Some of the participants are offline here with me. They will ask first, then we will go to the questions asked through the Zoom or YouTube. Yes, Manpreet.
Thank you, sir, for the wonderful talk. Sir, I have a doubt. My first question is, what is the lower limit of half-life of a nuclear state to be called as isomeric state? As I saw in one of your slides, that new nuclear isomers have half-life of 1 nanosecond, have half-life of 1 second, sorry. And I also saw that some isomers have half-life of 10 nanosecond or 1 nanosecond, but in new isomers have a half-life 1 second. So what's the exact lower limit of half-life of a nuclear state to be called as isomer?
Well, it's a perfectly good question. Thank you for it. But it's not defined. So when isomers were first discovered, people were particularly using neutron bombardments. So you'd put some sample in a beam of neutrons and then take it out. So you needed a few seconds at least to measure the radiation that was coming out after the bombardment. But as experimental techniques have improved, we've gone down to nanoseconds, where you can maybe have a pulse beam, and when the beam is off, you can look at the radiations coming from isomers as short-lived as a few nanoseconds. So really, the practical limit is mainly around a few nanoseconds in terms of discovery. But as our experimental techniques improve, there is no strict definition. I would say it's more important to think of the physics and whether the decay of the isomer is inhibited for some reason or not. And if there's a significant inhibition, then we're free to call it an isomer. So that doesn't really give a clear answer, but it shows that the science is evolving.
Sir, I have one more question. What are the conditions to call a nuclear state as isomeric state?
Well, it's so in the first instance, it's the half-life, but it then is worth considering whether it's inhibited for some reason. So the nuclear structure has some bearing on whether you call it an isomer or not. But maybe there's something more in the question that I'm not catching.
Okay. Sir, my question is, what are the conditions to call a nuclear state as isomeric state? As one of them is a half-life, is there any other condition to call a nuclear state as isomeric state?
Well, there isn't a simple condition like saying the half-life should be more than a nanosecond. I think that's the simplest. If you want a simple specification of a nuclear isomer, you can say it should live longer than a nanosecond. But I can think of examples where it's useful for shorter lived states, particularly the fission isomers, because the fission isomers were found when you bombard a lot of heavy elements with deuterons, alpha particles, you find slightly delayed radiations coming out, which are due to the fission from excited states. But some of these are less than a nanosecond. So the nanosecond cutoff doesn't apply very nicely to fission isomers in particular.
Thank you, sir.
Sir, I'm Dr. Sushil Kumar, and thank you very much for the wonderful talk. I have a question regarding the excitation of 8 electronic volt transition by the German group. So, what is the status of a nuclear clock based on this transition?
what's the state of the nuclear clock?
Yes.
Oh, the nuclear clock. Well, I'm certainly don't claim to have a lot of knowledge about nuclear clocks, but the the idea roughly is that you need to put the relevant material into some host and then to be able to excite it in a rather controlled way to measure the frequency. Oh dear, I'm showing that I haven't thought through an explanation of nuclear clocks that's very useful, I'm afraid. But I should read up about atomic clocks as well. Atomic clocks, I think it's the cesium clock,
Yes.
is the standard one, is based on a particular electronic state. So it's doing the equivalent thing with a nuclear state, and you really need to be able to manipulate it with lasers. So the very recent breakthrough in the last months, exciting the thorium-229 isomer with lasers, is
Yes.
a huge step on the way to making a clock. And yeah, so the reason it's good to do it with nuclei is nuclei are relatively shielded from the outside world, so to speak, compared to atomic electrons. So atoms are always bumping into each other, but nuclei are held apart by their atomic electrons. So the nuclear clock should be more stable by several orders of magnitude compared to an atomic clock.
Yes. Thank you very much, sir. Any other question from participant, please? There are a few queries received through the chat box of YouTube and Zoom. And the first one is, in the nuclear landscape, why most of the unobserved nuclei are neutron rich?
Which way are we going here? Is it gone? Here. No. I was right at the beginning, wasn't it? That one. Yeah, what's the best way to say that? It's some of it. I mean, it comes from several factors. One is it's quite hard to think conceptually, what is it that limits the number of neutrons you can put in a nucleus? Because if there's an attractive nuclear force between neutrons and protons, you can understand conceptually why there's a limit to the number of protons you can put in to a nucleus, because the protons repel each other. They're charged particles, and two protons have a big Coulomb repulsion. The Coulomb force is long range and the nuclear force is short range. So as you pile in protons, they're trying to blow each other apart. And when the nucleus is large, the nuclear force doesn't extend across the reach of the nucleus. So the Coulomb force wins and you get fission. That doesn't apply to neutrons. So the reason you can't add neutrons indefinitely is all to do with the quantum states that are available. And this is conceptually somewhat harder to think about. Right, but the other aspect is, if you see that nuclear chart, as you go heavier, it curves over to the right. In other words, you can put in more neutrons than protons. And that means that if you collide two let's get the argument the right way around. If you can collide two nuclei together, the product nucleus is neutron poor, so it's on the left-hand side. And so the left-hand side is more accessible than the right-hand side. You can't make the nuclei by colliding other ones together and fusing them. So it's got a lot to do with what you can make by fusion compared to other reactions that tend to just break the nuclei apart. Sorry, that wasn't a very simple answer, but it's a good question. I hope I at least gave you some insights to it.
One more basic query, I think you have already explained it, that what is the difference between the K isomer and shape isomers?
Right, so the K isomer is due to the orientation of the angular momentum with respect to the deformation, whereas a shape isomer is due to the change of the deformation itself. So it's a different physical situation. So you see, in fact, in that picture, it's quite relevant. The nucleus is what I would say is a rugby ball shape. Americans would say a football shape. I'm not sure in India how you describe the prolate spheroid that is illustrated there. But you can see that the orientation has changed relative to the angular momentum. You can actually do that through a shape change, so there is a connection with shape isomers. You could squash the nucleus into a sphere and then re-expand it with a different orientation, and you could keep the angular momentum the same. So the difference between them, when you look more carefully, is not so huge, but conceptually it sounds fairly simple. One is the angular momentum orientation relative to the nucleus, and one is the nuclear shape.
So thank you. One more queries. What is the recent updates in the gamma ray lasers?
Gamma ray lasers.
Yes.
So the big problem with gamma ray lasers is the recoil, because an optical laser, the emitted radiation can re-excite an atom, but in a nucleus, the gamma ray has so much more energy that the nucleus recoils, and so it has a recoil energy is lost from the gamma ray, and you don't get the resonant behavior. This is not solved, but I like to think that if Bose-Einstein condensates could be understood with isomeric states, then it might be possible to have some kind of coherent lasing action from a condensate of atoms, which maybe could avoid the recoil problem. That's a bit far-fetched probably, but there's not a lot of hope for any simple kind of gamma ray laser.
So thank you very much for your nice presentation. And at last, I would like to request our colleague, Dr. Ramandeep Kaur, to say a vote of thanks to the speaker plus participants who joined from the different institutes.
Thank you so much, sir.
Well, thank you for the opportunity.
On behalf of Department of Physics, Akal University, I would like to extend the vote of thanks. First of all, I am thankful to our Honorable Vice Chancellor, Professor Gurmeet Singh, for encouraging us and granting approval for organizing this webinar series at Akal University. I would like to express my sincere appreciation to our registrar, Professor Sukhjit Singh, for his invaluable support in making all the necessary arrangements for the webinar. A very special thank you to Professor P.M. Walker for sparing his valuable time to share his insights and knowledge with us during this webinar. Sir, your presence has enriched our learning experience immensely. We hope that we may have the privilege of hosting another session with you in future. I extend my appreciation to the IT staff of Akal University for their technical support and assistance in ensuring a seamless virtual experience for all the participants. In the end, I would like to thank all the participants from various institutions. With these words, we hereby conclude this vote of thanks. Thank you all once again for your unwavering support and participation. Thank you so much, sir.
Thank you very much.
So, Professor Walker, thank you very much. This is the second seminar on the nuclear physics. And I would like, if you could please spare some time in the future also, so we could have your another lecture for our undergraduate and postgraduate students. And this will be very, very useful for the students of our university plus students from the other institutes working in different places in India.
Well, very nice to be with you. I'll keep in touch.
Okay, thank you. Thank you very much.
Goodbye.
Bye. Bye.